Alrighty, good evening all. Hopping on a minute early just to do my regular little audio check to make sure everything's okay, and then we'll go ahead and begin. So, talking out loud just to hear if I can hear my own voice. Come on, checking my live stream on my phone. Looks like things are working. Let me check the audio. Come on, phone. Phone. Phone, why are you not connecting? I hope I can hear all right. I think my phone's just being silly. What if I just went directly to YouTube? Sorry, y'all. Come here. I hope I can hear all right. Okay. Sounds like things are working okay. All right, we are 7 o'clock on the dot, so let's go ahead and begin. All right, so welcome back, everybody, to another live stream, continuing on our series with working with the Titanic dataset. So just a quick, recap where we have come so far, and and give you a little preview of where we're going in the future. So far, the very first thing we did was just download the data set from Kaggle, talk about it, and do some exploratory data analysis on it. And then in our last stream, we actually did our feature engineering, and then you might recall that we saved off our clean data set with our clean features back into a CSV, and we are now ready to begin the predictive modeling process. So actually, you'll find that the predictive modeling process itself is not difficult, I guess you'd say. Like, it seems like by far the hardest part of creating a predictive model is doing all the feature engineering. And so I mentioned this before, it's a little bit easier to work with something like the Titanic dataset, where they give you basically the data on a silver platter. It's like, okay, you have these 13 features, have at them. In the real world, it's much more difficult because A, you're not given this data on a silver platter. B, you don't know exactly what data you need, and C, you may or may not have collected the data. And then also D, I guess, is the data may not be clean. So those four things are hard things. So actually, so we're going to continue on with our Titanic series for now, but I do have a different series in mind. And that is creating. So I like to listen to this podcast called The Water Cooler, and on that podcast there is it's kind of a comedy podcast, but it's got like different segments. And there's one guy named Kalen who does movie ratings, and so he will give a movie basically two different scores. One is a binary score, is like a yes or no, whether or not you like it, and then another one's a numerical value between 1 and 10. It's single decimal, so it could be like 5.3, 6.7, things like that. So I want to create a model that predicts what he might do movies. So I've actually been going back through the whole Water Cooler back catalog and collecting data and putting it all in this Google Sheets. And I have something like 200, or like not quite 200 movies reviewed. So not a ton of movies, but still quite a bit. And so that's going to be a project where we don't have a data set to begin with. And so the question is what features do we want to use, and how do we get those features? So that'll be in a future stream. I may take a break from the Titanic stream just to shake things up a bit, but for now we're going to continue along this. And so just to give you a preview of what we're going to be doing with the Titanic data set going forward as well. So tonight we're going to be building our predictive model, and we'll see how far we get with some of the stuff with that. And then in a future stream we're actually going to wrap that in an API. And so an API is something that we will be able to get inferences on new data with our trained model by passing it data into this API. So we're just going to do that locally, and then we're going to take that and wrap it in what we call a Docker container. And we'll talk more about Docker containers in the future. And then eventually I would like to get this all deployed out onto AWS SageMaker, and we'll even talk about SageMaker notebooks. We'll talk, and then maybe even go into Terraform. So lots of different things coming up. Hope you stick around. I'm putting them all in a single playlist called Titanic SageMaker on my YouTube. So if you don't, if you miss a stream for any reason, that's totally fine. go back and watch them. They're all in a single playlist. Yeah, so let's go ahead and jump into back into our Titanic dataset. Okay, so let me go ahead, switch over to screen sharing mode. Let me take a sip of water first real quick. So, hope you all had a good week so far. I had a good week. So today is actually sort of my Friday, actually. I'm not typically off on Fridays, but tomorrow, well, actually this whole week I've been working on and off with my dad on installing a new bathroom here in my basement. So actually, my basement, or my office here is in my basement, and so the bathroom is just going to be right outside the door, just like right over there. So that's going to be awesome. So like I'm not having to constantly run back up the stairs back and forth. So basically this, and then right next to this room is a spare bedroom with a bed net. So theoretically I could live down here if I wanted. And I even pulled out my baby fridge out of storage. You can't see it on the cam here probably, but right underneath my Megazord, it holds 6 cans of soda. So yeah, I'm gonna have a nice little space down here soon. So apologize. This is not what you came here for, so let's get back into the data set. Okay, so I started off our notebook here. So again, nothing here that you see on the screen so far is anything new. This is just a brief recap of what we did last time. So at the top here, we are importing our necessary Python libraries. So right now we just have the one. We will definitely be making use of more than one. Specifically, we'll be making heavy use of a popular data science library called scikit-learn. And we loaded in our clean data set. So you might recall that we took the X files, never even thought about that, and saved them out as the clean train.csv. And then we took the Y predictor values, which is the survive column, and then we exported those as well. So you can see here, just looking at with the head function here, that we can look at the first few rows of the data set here. So you can see this is all of our clean data. It's all good to go. And then we have our Y data set here. So the predictor values associated to these things. Okay, so before moving on, by the way, I do want to remind everybody that I do have the chat open, so please feel free to ask questions at any time. I am monitoring it down here. So I've got my primary screen up here, my like YouTube stream stuff down here. So please feel free to drop questions, and I will do my best to answer them as we continue along. All right, so let's jump into the first thing that we need to do. So, and the first thing that we need to do is what I guess I'm just going to call data separation. So whenever we are training a predictive model, it is always good to take part of that training data set and hold part of it on the side. Here, let me, oh yeah. Well, we hold part of it on the side just because we want to be able to use that as a validation data set. And so basically it's saying, okay, we have true values associated to, or ground truth values associated to this validation data set, and therefore we can compute validation metrics to ensure that the model that we are training is indeed performing the way we want it to perform. And so we'll get more into those metrics here in a little bit, but first things first, let's go ahead and separate out our data. So we are going to use scikit-learn's train test split functionality, and I don't remember exactly off the top of my head how to instantiate that. So scikit-learn train test split. So here we go. Okay, I always forget if it's because they changed it. It used to be under this cross validation, and now I think it's under this model selection thing here. All right, so I need to do, we're going to add another import up here. Import or from scikit, or I think it's just sklearn. Sklearn dot model split. And I think I did have to restart my computer like 20 minutes ago, so I think even though we see output values here, I don't think the kernel is actually loaded at all with anything. So just to start fresh, let's go ahead and clear all the outputs, and then we'll run these cells real quick. So boop, 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 and there we go. All right, so we have loaded our things. So in order to perform the train test split, it's pretty easy. So I think here, let me look at the example functionality here again. So yeah, so we basically are getting 4 different sets out of this data set. So we're going to get an X-train data set, an X-test data set, an Y-train data set, and a Y-test data set. So so they call it train-test split. I don't prefer that nomenclature, and the reason that is because you might recall that when we downloaded the Titanic data set the original time, that it also came with a test data set. So let me just show you that again if you don't remember that. So go into my repos, go into Titanic, going into data, and let's do an ls-a-ls. Okay, whatever. Okay, so you can see here the original data file that we were working with was called train CSV. We exported it again as clean train and then the YCSV. And then there is a testing data set. And so sometimes people do include like separate test data sets on things. And so I actually don't prefer this nomenclature of calling it a test data set when really when we're doing the split here, we're doing it for validation. So I am not, and you don't have to name your thing. You could name this purple, green, blue, yellow. I don't know. It would be super confusing, of course. So I'm going to call mine, so X train, X val for validation, Y train, and Y val. And so what we equals train test split. And so we need to pass in our respective data sets. So we're going to pass in the X data set, we're going to pass in the Y data set, and we can, so there are a couple options that people like to set in here. The only one I'm trying to remember where because I like to, you can select the training size and the testing size. I didn't realize you could select both. So actually, just a little aside, I do have another notebook that I had created the Titanic data set with before, and there's a reason I had it loaded up. I'm just curious what I did with this other data set for the train test split. Maybe I didn't get that fancy with it. Maybe I just kept it simple. Okay, so there we go. Yeah, I didn't actually define the split. I think the default split is it'll split it between, yeah, so a quarter of the data set will go to test, and then the other 75% will go to what do you call it? The training. So let's say, actually, let's go ahead and change it. So the first 2 parameters that we want to pass in here, of course, are our data sets, the X data set and the Y data set. But let's go ahead and set a test size to be different. So test size, so by default, it is segmented into a quarter of the data set. I am going to just instead do 20%, so that's 0.2. And then you might have seen the random state in here. So if you were to not set this random state and just run this over and over, it would constantly reshuffle what that train test split is going to be between the X and the X train and the Y validation, the X and the Y validation sets, training versus validation sets. So that's why if you wanted it to be always the same thing, like it's always going to be transformed the same way every time, then you set your random state. And it doesn't matter what your random state is as far as what number it is. So for you Minecraft people out there, whenever you start up a new Minecraft game, you might recall that your game automatically loads a randomly generated world. But if you want a very specific world, like let's say your buddy says, "Hey, I got this really cool world that I started," and you want to play the exact same world that he has or she has, then you will get their seed number from them. And so that's basically what this is doing, because then with Minecraft you can put in their seed number and then you get their same thing. So there's your Minecraft plug of the day. I love Minecraft. It's a great game. All right, so I just realized that you can't see the bottom there because my face is in the way. So let me go ahead and move my face up here. Hopefully you can see better. All right, so I'm going to set the random state. So a lot of people are going to set the random state to be 42, and you might be wondering why that is. I just want to check to see. Okay, because I don't know what all you could, how many, if there's like a limit to what you can put, like if there's like a 50 million bajillion, I don't know. Most people you will see put 42, and there is no reason for that, logically speaking, I should say. So the only reason that is if you're familiar with the book or movie Hitchhiker's Guide to the Galaxy, where the meaning of life, blah, 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 is 42. That is why people put 42 here. So if you ever look at anybody else's data sets and you see 42 there, that's what that means. But you could really have the random state equal 1, 2, 3, 4, 5. And like I said, I don't know if there's a max. Maybe there is, maybe there isn't. So I'm going to put a comment here I forgot to put. Splitting the data sets between training and validation. Okay, boom. All right, so just to make sure that it did split it out in the way in which we expected, we should be able to do a little, well, actually, let's just look at the X-train data set. Viewing the first few rows of the X-train data set, the first few rows of the X-train data set. And so X-train.head, head. Okay, so you can see it did randomly shuffle these, so you can see that the index values here are different. And then in the index values, unless you're trying to do some matching on like the y values, it really doesn't matter at the end of the day. In fact, actually, let's go ahead and look at the y data set, because it should be the same values, or like the same index values. So let's do a y train.head. And yep, there you go. So you can see 331, 733, 382, and so on. So it did separate properly. And just to make sure that we did get the 20% split correctly, we can do a little quick math, checking to see that the 20% split worked properly. So just doing a little quick math, so we can do the length of the X-train data set divided by the length of the just overall X data set, and you can see, it's not, this is not a perfectly clean data set that's easily divisible by like 20%, but you can see it got darn close. Like that pretty much is 80% right there. And yeah, so likewise, I would bet that if you did this with the Y data set as well, it would be the same thing. So in fact, let's just do it real quick. Y. All right. So yeah. So it's. Oh wait. Yeah. That's right. Because let's check out the val data set. Val. And then X. So this should be right at 20%. So perfect. So you can see that the test size worked. So like I said, default. If you don't set this, it will set to 25% for the test data set. And just to show you, just real quick, like that it really does shuffle every time if you don't set this random state. Let's go ahead and delete this random state out temporarily. And rerun these cells. Okay, so you can see we get the values of 10, 800, 145, 82, 366 here. So let's go ahead and run this one more time. We get new values again. We get new values again. All right, and so, but if we were to set the random state equals 42. All right, so you can see that we are back to the original values that we had before. And if we were to run this again multiple times, run it again, same values, running it again, same values. So this is important, especially in the data science world, if you really want to make sure that people are following the same procedures and that you use. So not just the data science world, but in the science world in general, when you perform experiments, and this is why we call it data science, is because we want to follow like the scientific method as closely as possible, and making sure that we have like statistical significance for the trends in our data. We want to have as much reproducibility as possible. So like, let's say science in general, if you make a discovery about a new breakthrough medication, you want to be able to prove to your fellow scientists that they can also produce the same results. And in order to produce the same results, they need basically the same methodology. So they need to be able to use the same tools, same metrics, same everything. And so that's the idea here with the random state here, is we set the train versus the validation to split the same every single time. That way, if if another data scientist friends comes along and wants to validate our work, they can, and it will be the same. Alrighty, so that is data separation. So let us, what do we want to do next? Let's go ahead and start off the predictive modeling process. So model. Well, actually, I'm gonna, let's do. This is sort of the what do you call it? The modeling process, but we're going to do something called hyperparameter tuning, and this is going to make sense here in a second on what this is. So whenever we work with different algorithms, all these algorithms that we use are based in math, and so they have different features or like different features is. I'm trying to not use the word featured so I'm not confusing the thing here. They have different like mathematical attributes, I guess, where you can set different things that would alter the algorithm in different ways. Well, I guess they're hyperparameters, so I don't know why I'm trying to find something fancy. So whenever we actually use one of these predictive models, it is good to perform what we call hyperparameter tuning to find what are the best values for your model. That way, whenever you actually formally train the model, you are ensuring that you have an ideal algorithm. So the first question you might be wondering is, okay, what is the ideal algorithm to use? And honestly, so let me step back here for a second and remind you all that I am a machine learning engineer, not a data scientist, so I am not super perfect in these things. If any of my coworkers are on, any of you, and if any of you are watching, please forgive me, because I might be botching this a little bit. But anyway, as far as like when I've talked to my coworkers about like how they select algorithms, the answer is there's not really a one-size-fits-all kind of answer here. Like, granted, so you do have algorithms that do specific things, but like it's not like one is necessarily inherently better than the other every time. And so what I mean by that is, so this is what we call a binary classification problem, and we call it a binary classification problem because the Y predictor value is binary. It is a 0 they survived, 1 no, 0 they did not survive, they died, 1 they did survive. So binary classification, and so we have specific algorithms that are specifically tailored toward binary classification issues or problems. You may have different algorithms that tend more toward regression problems. So if you might recall, when I was talking about the movie rating algorithm that I want to create, that 0 to 10 sliding scale of where you have kind of like continuous values up and down the scale. And I know actually that one's a little bit discrete because there is no more than like one decimal place for that. But anyway, for continuous values, you'd want a more of a regression-based algorithm. And so I am not. So what a data scientist would do optimally is basically, for our binary classification issue or problem here, is they would take every or at least 5 or 6 different algorithms and throw the data set through all of them and see which one performs the best. Literally, that's I think the best way I can explain it. And again, might be botching that a little bit or oversimplifying it a little bit. But for our particular thing that we're going to work on here, I'm actually not going to worry about trying to focus on too many different algorithms. Tonight, I'm going to focus on one, just so we can understand the one pretty easily and understand what we need to do with that. All right, so, and the one that I'm going to use is what is called a random forest classifier. So again, stepping back for a second here, so we have our different algorithms that people can use: binary classification, multi-class classification, regression, unsupervised clustering, and I'm not going to get into all those fancy things, but we're doing binary classification here, and I lost my train of thought. I have no idea what I was going to say. Let me take a step back. I'm doing I don't normally do this much talking. Like you can even ask my wife. I'm not a talker. I'm kind of an introvert actually. I prefer being in my little dungeon playing my video games. So I have 100% lost my train of thought. So hyperparameter tuning, what were we talking about? Random forest classifiers. Oh, okay, now I remember. So you have some algorithms that are more, for lack of a better term, bare bones, or more simplistic in nature as far as the mathematical algorithms go. And so, and then you have what are called ensemble models. And what ensemble models are basically doing is they are combining the best of different kinds of algorithms and putting them together into like a nice Frankenstein, I guess you'd say, of algorithms that work better. And this isn't to say that ensemble algorithms always perform better than just like a like a run-of-the-mill algorithm. It really depends, but I will say it does seem to be that most of the time that an ensemble algorithm seems to outperform other algorithms. So, for example, a more bare bones algorithm would be something like logistic regression for a binary class classification model, whereas a random forest classifier or AdaBoost or XGBoost, those are ensemble models that might perform better. And so that's why I'm purposefully choosing the random forest classifier. And yeah, so, and one other thing before actually jumping into our hyperparameter tuning that we're not going to do tonight is to note that if you use different algorithms, you will have to do what we call feature scaling on the data. So for random forest classifiers, I think you don't have to perform the scaling, but I think you do have to perform the scaling for logistic regression. And so what that basically means is, so like let's look at the data right here, and let me move my pretty face on down here. It is basically stating, so if you notice, like most of our data in here is like pretty like low in range. So like when I mean low in range, I mean like, so P class you just have 1, 2, 3, sexist binary 0 or 1, and then you like pretty much the rest of these are binary. But you notice the fair column has quite a disparity between the range here. And so when I mean feature scaling here is, depending on the algorithm that you use, this wider disparity of a feature here versus one of these others could unfairly bias the algorithm a certain way. And so what we can do is we can basically get all the data onto the same scale. That way all the features are being treated fairly. And there's a simple way to do that with some scikit-learn things. So there's two different ways to do that. There's standardization and normalization. They're both a little bit different. Standardization basically takes all the features and squeezes them between -1 and 1, and basically is using the standard deviation of the features. So the standard deviation for the sphere column, I don't remember the values of the sphere column. I'm not going to look it up. It basically, I'm going to imagine, just looking at the values here, let's say that the mean is 22. And then the standard deviation is, I don't know, $5. So like this 31 value would be 2 standard deviations away. Whereas the other one, I don't know, maybe I'm explaining this pretty poorly. I'm not very good at standardization versus normalization. So I do know standardization in particular has to do with standard deviation, whereas normalization squeezes the values between 0 and 1. And I think the reason you'd want to choose one over the other is if you have like large outliers of data. So like the large outliers of data bode well better, I think, for standardization with the standard deviation, whereas like normalization, if you try to squeeze all the values between 0 and 1, then the outliers can really like kind of screw with that. And you know, the reason I'm selecting random forest classifier again is because I don't want to have to do that. And the only reason I don't want to have to do that is because I'm pretty bad at it, clearly. and I'm pretty sure I'm not explaining it perfectly. So just give it a goog, as Pete Holmes would say, comedian Pete Holmes. AKA just Google it if you want to learn more. I'm sure there's great articles that explain standardization versus normalization better than I just did. But for our data set, I am not going to worry about that. But if I did, it would be probably before I did the split here. When I loaded in this data set, I would do the standardization. And just to show you in the scikit-learn documentation, so let me do scikit-learn standard scaler, I think it's called. Yeah, standard scaler, there it is. So you can look at your documentation, and it's pretty easy to do the scaling. Oh, look at that! It appears that I'm correct, at least with talking about the mean here, because this is the formula for standard deviation. So if you want to use this, let's look at an example, because sometimes the examples are easier to look at. So it's kind of like our one-hot encoder or our imputers that you might recognize, and that is, so you instantiate the object itself, then you fit the data to the object, and then you're able to perform a transformation appropriately. So you can do a fit transform. Yeah, so that's that if you want to use that. And I can't remember what. So standard scalar is the one I know better. I don't know. I'm sure there is one for normalization. I can't remember. Scikit-learn, normalization. Yeah, I think this is just normalize. Yeah. Okay. So yeah, if you want to learn more about those, definitely look at those. I'm not going to focus on that tonight. I've already talked about it way more than I thought I would. So let's jump back into here. So like I said, we are going to use the random forest classifier, and so scikit-learn also has a default random forest classifier built in. So we are going to make use of that. So scikit-learn random forest, not regression. We want a classifier because this is a classification algorithm. So you can see it's even part of. It even has it under the category of ensemble models. Okay, let me take a quick drink here. Very nice. All right, so you can see within our documentation here that there are a number of different parameters that you can set, and you don't have to set all these, and I'm not going to set all these. And so you can set all of these things, and you know, honestly, I'm not great at understanding like what is necessarily best practice for hyperparameter tuning per se. Well, you'll see what I mean here in a second. So, but these are all the options you can set if you want to set. So the first thing I'm going to do is I am going to load in this object, this Python library here up at the top from sklearn dot ensemble import our random forest classifier, classifier. Okay, there we go. And I'm going to run this cell again, so we definitely load that in. All right, and so when I come down here, I am going to instantiate the random forest classifier object. Instantiating a random forest classifier object. So I'm going to call this RFC being short for random forest classifier, RFC grid search, and you'll understand why here in a minute, equals random forest classifier. Okay, I'm gonna be just being transparent with you all. Like I said, I'm not a data scientist, so I don't do this stuff on a daily basis. I can't remember the exact syntax on how to do this. So, and I know I could Google it, or I could just, like I said, I've done this before for another notebook, so I'm just gonna go look at what I did here. Okay, so I had to. All right, so I just instantiate it without setting any parameters. And then I set the params up here. Okay. All right. So let me come back to here. So I actually don't need to put any parameters in here, and this will make sense why here in a minute. So so I'm just instantiating the object. So let's go ahead and do that. And so for hyperparameter tuning, we are going to set a range of values through which we're basically going to put the model through the ringer with all these different parameters, and then it's going to test out different things to see, like, okay, which one seems to be performing the best. And so the first thing we needed to do is define the grid of parameters. So defining the parameter grid for hyperparameter tuning. Parameter tuning. I normally type a lot better when people aren't looking, so let me go ahead and slide my face up again so you can see what I'm doing. Okay, so I'm going to call this params equals, so this is going to be a dictionary of values. And so what this dictionary of values is going to be different values that help support any of these features. And so we can do multiples of the features, we can just do one or two, we could do all of them. I'm not going to do all of them, and I'll explain why here in a minute. So in fact, I'm going to be a little bit lazy here. I'm just going to copy this here, just because this is quite a bit of typing, and yeah, so I'm just going to copy this here, and let's talk through this. So what this is basically doing is, you'll notice that, so these are different parameters that are options for the random forest classifier. We could have selected more, we could have selected less, and these are the values that we're going to basically put the model through the ringer with. So I have 3 different values for each of these, and so this is where I was saying I don't know what best practices are for actually defining these values. These are arbitrarily defined values. I just thought, you know what, I'm going to try out n estimators equals 10, 50, and 100. I think I've tried before more, so you can put as many as you want. You can put 50, you could put 5 of these different values, and they don't even necessarily need to be consistent. You could put 5 values for a number of estimators here, 2 different values here, 30 different values here. I just kept it all 3 through 3 and 3 just because it's simple. But, so, this is the reason you don't want to do this. And well, let me go ahead and keep going. All right. So we are going to, in order to help understand what are the best parameters for hyperparameter tuning, we are going to use something called scikit-learn's grid search. And so grid search is going to perform, it's basically going to take this grid of parameters that we have, and then it's going to train the model using all these parameters every single time. And so that and that's why it can take really, really long time if you select a lot of different values. Because basically, so like the first go around is going to put n estimators equals 10, min sample split equals 1 or 2, min sample split equals 1, max depth equals 10. And then the next time it's going to go 10, 5, or no, it's going to go 50 to 110, 100 to 110. So what is that? You statistics people can do the permutations or the combinations of how many different combinations there are. But basically, the more of these values you have, the more combinations you have, the longer it takes to run. And let me tell you, I think this is long enough to run as is. So I actually haven't tried it out on my new computer here. I think I mentioned before that I did get a new Mac Mini a couple weeks ago, and it has the new M1 custom Apple processor in it. So I am very curious to see if this is going to perform better than my last computer. I think it will perform better, but I don't think it's going to be like lightning speed. So that's why I say be cautious with what parameters you select, because if you went ham and just selected every single feature and you gave them all 5 values, you could literally have your computer running one solid week to find the best grid search parameters. Maybe you do want to do that. I don't know. At some point, it seems like it would be overkill. Like the accuracy of your model probably isn't gonna like substantially increase, but by like doing a crazy amount of like hyperparameter tuning. But yeah, so like I said, scikit-learn, one of our best friend libraries, does have this grid search. So let me see how you instantiate that, or I could just go back and look at my other notebook. Let's look in here. So just to show you, these are the parameters here. So what we are going to be doing is we are going to be passing in the estimator object. So the estimator, so you might hear it like this has actually never been explained to me, but this is the way I understand it. But an estimator is basically an untrained model that we've just instantiated. So in this case, the estimator is going to be the random forest classifier that we have not done anything with yet. The param grid is obviously going to be that parameter, the dictionary list of parameters that we already set. And then scoring, I don't know if I want to mess with that. I don't think I necessarily mess with any of these other ones. So actually, like I said, I'm going to go, I'm not going to beat myself up over this. I know that I have done more stuff with this in the past, but it looks like I kept things pretty simple here. Okay, so let us go ahead and we're going to need to load in our grid search object from scikit-learn here. So I'm just going to copy in here what I did. Okay, so it looks like a grid search is part of the model train, or the model selection library. So model selection, coming back up here, throw in a comma, and grid search CV, or CV. What does the CV stand for? I don't even remember. I don't even know why they call it grid search necessarily either. I kind of just wish they called it the hyperparameter tuning guy or job. CV, let's see, CV. Oh, cross-validated. There you go. That makes sense. Okay. All right. So I'm going to call this instantiating the grid search CV object. All right. I'm going to call this grid hyperparameter tuner equals grid search Okay, and so I'm going to stop right there for a second. So if you might recall, Jupyter is actually smart enough to know that like if you start to type something and it sees that like it's relevant to something, then you can hit tab and it should autofill for you. But in this case, it didn't. So, okay, well, I mean, it does sometimes. So grid search, CV, and so the first thing we want to pass in is what was it called? The estimator. So the estimator equals RFC. Now I know this one will work, grid search. So I know it auto populates variables. I thought it auto populated functions as well, but I might be wrong, or apparently I am wrong about that. And then the param grid equals the params. So that is our this Python dictionary that we established up here. Okay, just want to make sure that I got that right. Okay, so now that we have instantiated our object, grid search CV is not defined. Did I not run this cell again? Grid search CV. Okay, maybe that's why I did not populate. Now I'm curious, so let me just type it in. Grid search. Yeah, okay, that time it did work. So okay, maybe I'm not crazy and I just the first cell I forgot to run the first time. My bad. Okay. Oh no! Are you all still there? P3. No! Oh my gosh. Okay. Sorry about that. I accidentally locked myself away. I hope the stream is still working just fine. Alright, so now that we've instantiated the hyperparameter tuning object, now we are ready to put in our terrain. I think you... how do we use this guy again? Like I said, it's been a while since I've used this, so I can't exactly remember how it's done. In fact, let me just go over here. So, do we just put in the validation data set as well? Okay, so we are going to fit the training, fitting the training, the X train and the Y train to this object, and it's going to do its thing. All right, so let's go ahead and do this. So running the hyperparameter tuning job. So by the way, one quick thing, you'll notice that, and I've mentioned this before, I do love to heavily annotate my code with comments. In Python, that means starting it off with the pound sign. I do like to put a space in between the pound sign and the first letter. Most people do that as well. That's a common practice. And one thing that I particularly like doing is I like to start off my like my comment with a I'm not an English major, so I apologize. It's whatever the verb is that ends in ing. So you can see all of these are checking to see the 20%, instantiating, defining the, instantiating the, running the, and I think it's just nice for consistency's sake. You don't have to do that, but I think it's my personal best practice, and yeah, take it or leave it. All right, so running the hyperparameter tuning job. So hyperparameter tuner dot fit. So we're going to fit the X train and the Y train data set. All right, so hopefully this is going to work. All right, so you can see I'm getting a bunch of different warnings right here. So these warnings don't the warnings, you know, warnings are warnings. Like it's basically saying that I did something not necessarily super correct, but it's fine. Like it's still working just fine. You can see, so for every time this is running, it is basically creating a new model. So that's why you see so many of these different combinations here. And wow, I can't believe it. It's already done. Cool. Hello, Mac Mini. I can't believe it just blasted through that quickly. There is a way to suppress the warnings. In fact, I'm going to go ahead and do that. And I noticed that in here. So if you want to suppress your warnings, that way you just don't have like a mess of stuff, you can do import your warnings here and then filter warnings and then just ignore. So I'm going to put this at the top of the notebook. And I can't believe that ran that fast. Seriously. So my last laptop was an early 2019 MacBook Pro, 13-inch. And it was a nice computer, obviously. And I think it would have taken at least 5 minutes for it to run on there. So I am astounded. And again, we kept it pretty simple. Like usually these things kind of run forever. So I want to see this again. So I'm gonna put in the warnings, and I'm going to see how long it took to run. All right, so by the way, if you see the asterisk here, that means it is running, and then when you see the actual number appear up, then it'll be complete. All right, so let me go ahead and type out the comment for the next one. So once this is done, we can then view the parameters that ended up performing the best, and then those are the ones that we're actually going to use for our formal training. And so this is just basically showing us the same thing that we instantiated here. So this is no new information. So in order to view the best hyperparameters, we have to go ahead and print those out basically. So viewing the best parameters from the parameter tuning job. Okie doke. All right, so in order to do that, hyperparameter tuner dot, I think it's best params, and I think it's got like a weird underscore at the end there. Okay, so there we go. So basically, all right, so if we come up here, these are the parameters that we defined, and so it went through the whole permutation of all these to see which one it thought did best, and basically at the end of it, this is what it came up with. So it's basically saying use these basically, and so I want to say no, I'll just manually type these out. So because I was going to say I could export these out as like something that I could just drop into another random forest classifier for my formal training and be on our way. So but it's okay. So this is the hyperparameter tuning job. Hyperparameter tuning job complete. All right, so this is pretty simple. So again, we just did the one model though. We kept it pretty simple with our param grid. We could have used more features. We could have used more values. And that just would have taken a lot more time. And I would advise you to take at least a little more time to try out a couple different algorithms. But we're going to keep things simple here for our own sanity and just to keep things moving along. All right, so now that we have completed the hyperparameter tuning job, we are ready to begin the formal model training. Woo! And you're going to see how lame this is. Like the very first time I saw this, it's not lame. It's just that like when you think about artificial intelligence or machine learning, the first thing that might come to mind is something like Skynet or I don't know, HAL from why am I blanking on the name? The movie, Stanley Kubrick, Space 2001: A Space Odyssey. There you go. But really, like, so this is still technically machine learning. It's just fancy math going on under the scenes. So what you saw here that we fit the training and the X-train and the Y-train data set to the hyperparameter tuning job here. We're basically going to be doing the same thing for training here. It's just that instead of fitting it to a grid search object, we're going to fit it to the model directly. So let's create a new little header here. Let me zoom out so I can find my markdown because I like. So best practices for a notebook. It doesn't matter if you want to do this or not. I personally like to break down like major sections with headers like this, so you can see that this section is the hyperparameter tuning. We're going to call this one model training, and I like to do it as a second level header, which is 2 pound signs. Third level header is 3, 4, 5. I think 5 is the max you can go, and then if you try to do 6, then I think it just interesting. Wait, 1, 2, 3, 4, 5, 6. Interesting. I thought it just, yeah, okay. Maybe it goes 6 levels now. It only went 5 for before. I don't know. Okay, but I like to do 2 anyway. So now that our hyperparameter tuning job is complete, let's go ahead and instantiate a new random forest class for our object. So instantiating a, oh my gosh, I can't spell. Instantiating a new random forest classifier object. All right, so I'm going to call this one RFC model, so random forest classifier model equals, okay, so above you might recall that we didn't put anything in the parentheses here. Now that we do have our parameters defined, I'm actually going to populate this here. So n estimators equals 50, and then you don't have to do it on a new line like this. I just like, again, there are certain things you can do with coding that are just like for like aesthetics purposes. So you can see that I do a lot of aesthetic kind of things, and that is adding the comments, putting things on new lines. So in case you're curious, there, if you remember back to your college days of writing papers or anything, you might recall that your professor had you write things in like the MLA format or the APA format. So coding actually does have something like that called PEP8, PEP-8. I don't care for it. Just being honest, it's not bad. Like, it's just, but it's not to my preference. So, and actually, you can download like this tool called. Why am I blanking on the name of it right now? It's basically it's a linter, code linter. Sorry. So the code linter, you could basically run your, you could take your code as it stands today, put it through this code linter, and it will. So in Python, it's called pylint. It will give you back a score of how well it thinks you did, and it will like tell you ways you can in which you can improve. And like, so the reason I hate PEP8 is because I think I do a decent job of cleaning up my code and making it very readable, but I always score like a 40%, which, or a 4 out of 10, which is in schooling terms, that is an F. I am failing, but I don't think I'm failing. Yeah, so sorry for the deviation there. All right, so let's start to type more of this in. So max depth equals 20, min samples split, min samples split equals 10, and then what is the other one? Max we already did, min samples leaf, min samples leaf. And I actually do know the random forest classifier algorithm pretty decently, because one time I had to code it by hand. And actually, that is one thing that is interesting. If you ever go into like a formal data science program, and I only know this from talking with a number of different interns that went to Purdue, interns that went to the U of I. It's interesting that the professors there actually do have the students code these algorithms by hand, usually using C, the programming language C. I personally don't know how valuable that is. Just being honest, like. Because I understand how, like, what the math is doing behind the scenes here, but like I said, at the end of the day, because we don't know exactly which algorithm is going to be best, we end up, and it's so easy. You can see here, it's actually pretty easy to fit or train a model, because all we're doing is just basically instantiating an object and fitting the training data to it. Like, why not put it through as many algorithms as you possibly can? And in that case, it doesn't. In my opinion, it doesn't seem to matter. That you understand what the math is doing underneath. I think it's more important that you have a conceptual understanding of like what these classifiers are doing and when they're used for. So like needing to know, for example, random forest classifier, logistic regression are binary classification models, whereas a random forest regressor is obviously a regression model. I don't know how helpful it is to actually know the math for these hyperparameter tuning kind of things. Yeah, so, but there are lots of great videos out on YouTube or Udemy or any place. If you really want to know more about that, go at it. I personally don't think it's the best use of your time, especially when I talk to some of these interns and they tell me, oh yeah, we spent this much time coding an algorithm, but I have no idea how to actually use this model in production, which is kind of sad. It's like, isn't that the purpose? Like, we're not just creating these models to not use them, right? Okay, so this is instantiating the object, so let's just go ahead and run that cell. All right, and now we can perform our model training. So performing the model training. So model training. Okay, so RFC model dot fit. So we're going to fit the X train and the Y train data sets to it. And like I said before, above we were basically doing the same thing that we're doing below, except we did a number of different permutations of all these different values. In this case, we only have one straight set of values, so this should be actually really quick. So let's see, 3, 2, 1. There you go. Look, it was almost instantaneous. So the model is trained now. We now have a trained model. Cool. So before we go and save it out so we can use it for later usage, let's go ahead and check it out against our validation data set that we went ahead and wanted to check against. So I'm going to create another header again here. We're going to call this model validation. So model validation. And so what we want to do with model validation is we are going to take our validation data set. So as you might recall, so we have our XVal data set. So the XVal data set here has all the features except for the survive column. We're going to put what we're basically going to do is we're going to put it through this trained model, and as you might recall, we do have the Y validation data set, which is what we call the ground truth. So we know that these are the legit values in which we're expecting, and then we can calculate metrics to see how close were we with the predictive value versus the ground truth actual value. And so there are a number of different metrics that one can use to help with this assessment. So obviously the easiest, most simple one is just like straight accuracy. And so when I mean accuracy in this context, I mean like how many times, what percentage of time did the model get it correctly? And so that's a pretty simple calculation. But we can go even deeper than that with accuracy to do more things like precision versus recall, and these are some mathematical terms that I'm not going to explain tonight, but you're more than welcome to look them up. ROC, ROC, AUC, I don't know if I'm pronouncing the acronym correctly, but it's what does that stand for? Receiver operating characteristic area under the curve. I think I messed up the first part on that, but anyway, again, our friend scikit-learn has the ability to do that pretty easily. So again, just to save time, because we're coming up on an hour already, I'm just going to look, because I already did this for my other notebook here. So scrolling on down. Oh, one thing I did want to bring up that I thought was interesting, and just to show you, like if you recall from our feature engineering last time, more than one way to skin a cat, more than one way to do things. I totally forgot that in this section here, I actually did do something with the cabin data set, and that was apparently there was something within the cabin that like the last character indicated whether or not like what your section you belonged in, or maybe it was the first character. Yeah, the first character defined what section you belonged in. And so what I did was, that's what this is doing. So this string, str stands for string, and it's looking for the first character here. And I basically engineered a new feature that said like, okay, this is the first character, and if you didn't have one, then I filled the nulls with no cabin. And so it's interesting because I don't know if that really would have a huge impact on the model, but it could, and that's where feature engineering can be really important. It is by far the most important part of the whole predictive modeling process. Okay, so what was I saying? Coming down here, so I did the train test split, we did the data modeling, we fit the thing, we got the best parameters, we trained. Okay, so let's do our model validation. Okay, so I don't want to cheat too much here. All right, so the first thing that we're going to do is we are going to get our predictions from the X validation data set. So in order to do that, all right, let's type in here, getting predictions on the XVal data set using the trained random forest, or I'm just going to call it trained RFC model. Okay, in order to do that, so I'm going to call this val preds for validation preds, or validation prediction. Predictions in the data science world is often shortened to preds, just because it's easier. All right, so I'm going to do RFC model. So this is our trained model. So fit. It's not transform. It's predict. Okay, predict XVal. Okay, and all right, so that's done. Let's go ahead and look at those real quick. Preds. All right, so these are all the predictions from our validation data set, and so I'm just comparing them just visually. Let's see if we can do that. So y val. Let's do survived. Okay, I'm starting a little bit raspy here. Okay, so you can see just visually speaking. So it got the first one wrong. Got the next two right, got the next two right, and the last two correct. So, but we obviously, you know, we got, I don't know how many values here, at least 100. Well, I don't know how many there are. But in most cases, you're going to have thousands of these predictions, and obviously you can't do the one-to-one back and forth. Did this one get it right? Did this one? So this is where I'm talking about, where the metrics are immensely helpful here. So in order to do that, the first thing I need to do is import those metric objects from scikit-learn. Again, I'm going to keep it pretty easy here and just copy over here from my other notebook. So these are 4 different metrics that we can calculate, and so actually, and I'll explain these here in a second. All right, so I'm going to load these in here. All right, so we have, like I was saying, the ROCOC score, the accuracy score, and the confusion matrix. So I'm not even going to attempt to calculate or explain the ROCOC score because I honestly can't remember what that's calculating. But I can say the confusion matrix. The confusion matrix is actually displaying the precision and the recall and of the model. And I thought I had F1 in here as well. F1 is another score that people can use. Apparently I don't, but that's okay. I just want to get a couple for example. Okay, so let's come on down. All right, so getting the metrics with the validation data set. Okay, so what we are going to do, I'm going to cheat back on my other notebook here just because I can't remember off the top of my head. Again, this is not something that I personally do on a daily basis, which is why I struggle to remember this. All right, so I'm going to do the val accuracy equals, so what was that called? Something accuracy. Accuracy score. Accuracy score. SE score. Oh, yeah, that's why it's not auto-populating, because I got to run that cell again. And again, this is why it's not great to do things in like have everything do in a Jupyter notebook, because if you run these cells out of order, then you're in trouble. So that's what at the end of the day, like if I were to clear this out and restart again, because I've done everything pretty linearly, I wouldn't be in trouble. But I have seen issues where like somebody will train a model in a Jupyter notebook like this, and then fail to mention, oh, I didn't run. It's not linearly. I ran this cell, and then I ran this cell, and then I ran this cell, and then I ran this cell up here, and then so yeah, and it can kind of get to be a jumbled mess. All right, so accuracy score, and I'm trying to remember. Do you pass in the true values or the predicted values first? Let's look. So scikit-learn accuracy score. So that'll tell us here in a second real quick. Okay, so we want to pass in the true values first. So the true values, of course, are the X validation data set, or no, I'm sorry, the Y validation data set, Y val, and then we're going to pass in the val preds. And let me run this real quick just to make sure that this worked. Val accuracy. Okay, that worked. All right, so we're basically going to do the same thing for the other values here. So val roc equals accurate or not ROC AUC score, and so same thing here. So we pass in the true values first, followed with the predicted values. So and then finally the val confusion or confusion matrix equals confusion matrix Y val preds. Okay, preds. Okay, so behind each of these different variables here is the actual numerical values. So let's go ahead and print these out appropriately. So printing out the validation metrics. So I'm going to do a print, and then I'm going to do what we use as an F string. So what the F string here is basically saying, like, if you were to just do like a straight print, so like within the quotes here, so that's just going to print out what you want in here. But let's say you wanted like the validation accuracy here. So like let's say I want to put val accuracy right here. Obviously, it's just going to show a character representation of it. So in ye olden days, what people used to do is they'd go put hello this is my, and then they end the string, and then they do this business of doing this plus sign, and then doing the val accuracy, val accuracy. Oh my gosh, there we go, and then do another plus sign here, accuracy score. And so I mean it's can only concatenate string. Okay, well I screwed something up here, but it was something similar to this in the past. So and this isn't difficult to type, but using F strings are a lot easier. So what this is, so at the beginning here we put F, and then within our quotes here, then we can say accuracy score, colon, and then within curly braces here, we can put in the actual name of the variable that we want to represent here. So that way it kind of just shortened things down, and I personally love using F strings like this. So let's do this for the other guys here. So accuracy score, ROC, AUC score, quote, curly brace, rock. Oh no, it's val rock awk, val rock awk, and I don't even know if that's the right way to pronounce those acronyms. That's just the way I do it. Okay, and then print F confusion matrix, and I think I like to do this one on a new line. So if you want to do a new line in Python, it's just the \n, and then val confusion matrix, and I think I did that right. Quote, quote, quote. Let's go ahead and run this cell. Uh-oh. Yeah, I thought so. I thought I was missing something in here. Oh, yeah, that's the one thing I'm not wild about F strings about, is sometimes, like, if you type in a quote, it tries to, like, help you out by putting another quote in there, and then I do this business of accidentally running a thing with two quotes. All right. So, okay, so there we go. So we got our accuracy score, which is 80%, which is not bad, but not great. Rockhawk score is more or less the same. And then this is our confusion matrix that has different representational values representing the precision versus accuracy and things like that. So not going to worry about explaining that tonight, just to show you that you can do this. And these scores are important to assess. So these are the scores that if we had multiple different models that we were trying to train against, like multiple different algorithms, these are the metrics that matter. Because obviously you want something that's going to have the highest accuracy score, the highest ROC, AUC score. So now I'm curious, just looking at my other model, because I did train it a little bit differently using that cabin feature, and it looks like it fared pretty much the same. Like it looks like AUC was a little bit worse, but maybe accuracy was a little bit better, or it's dead on the money actually. No, it's a little bit different. But yeah, it's pretty close. And of course, algorithm is not always just the magic touch either. Like, it's not like if you select a different algorithm that things are going to get better. Sometimes you really do just have to go back to the drawing board with your features, do more feature engineering, gather more data, or even conversely, take out some data. Maybe you have some confounding variables in there that are doing some things that you don't want it to do. So I'm not going to worry about getting this accuracy any higher because I don't care. We're just having fun here. But if I was working in a business, if I was making medical precision equipment and I was making, for example, I don't know, some sort of, this is going to be a really bad example, but like a heart monitor, a heart whatever, and it was using some sort of machine learning to do the actual predictions. I want that thing as accurate as possible, clearly. Like, I don't want that thing failing, because obviously, I mean, I don't want to get sued. I mean, that's one thing, but moreover, I'm a caring person. I don't want people to get hurt. So in this case, for medical equipment, 80% is just terrible, and I would never, ever, 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 ever take that to market. But, we're not going to concern ourselves with that tonight. So the reason I did want to bring up this other notebook, because you might be wondering, underneath the hood of these models, like, is there a way to tell, like at the end of the day, like, which of the features were more valuable for a given model? And there is a way to do that, and that is through something called, there's two different things called SHAP and then LIME. And so these are other mathematical things based in game theory. Honestly, I'm not well suited to talk about the math underlying them, But there are Python libraries that help associating with that, and basically what these libraries will do is it'll help tell you the explainability of the features to like tell you which features matter the most. So this is my visualization for SHAP in particular. So you'll notice here that the most predictive value, or like the best predictor values, appear to be sex male versus sex female. And I think in this particular data set, I actually did separate these out into two different features, which is why they're represented twice. They wouldn't be represented twice in the other model we did because there's only one feature for that. If you had a third-class ticket, if you had a second-class ticket, if you had parents or children, it seemed to be more predictive values. And then these other features down here seem to not like be as predictive. And so that's SHAP, and Lime does something pretty similar. And then why are the visualizations not showing up in here? Huh. Okay. Well, I have a blog post out there. If you just search within Medium, there it's published toward Data Science that will show like the visualization for Lime as well. And so basically, coming back up here, you can see that the most predictive values were basically like between. So I actually selected it for two different people here. So person 1 and person 2. It seemed to be that the sex and the age of the person mattered the most. And intuitively speaking, this is what we talked about whenever we were doing our feature engineering. You know, if you think about the rationale of people getting off the Titanic, it was most likely women and children getting off the boat first, and that appears to be validated by like SHAP and Lime here. I actually think Lime has some better. Actually, let me go ahead and Google that because I think Lime had some better visualization, and I know I put the visualizations in the blog post. So, SHAP Lime. I wish Medium had a better way to search your own posts. I always just have to scroll down and keep looking. So, I know I did it like a year ago. Alright. Talking to fill the void so we don't have dead air. Because that's what we do in the streaming world, I guess. I'm not really a streamer. I'm not like a video game streamer or anything like that. So I hope I didn't pass it. I'm not very good at talking and doing other things at the same time. This is a skill that I'm growing in. So I hope that I'm. If you've been watching these live streams today, that I'm getting better and better each time. I think I'm finally happy with the lighting at least. So the very first one was like I looked at it, I was like, oh man, this is super dark. And I had. Oh wait, I was gonna say I thought I had passed it, but here we go. So I did this on September 13th, 2020, so almost a year ago today. That's kind of cool. All right, so SHAP. All right, so there's SHAP. We saw those before. So these are the Lime tables I was talking about. And I actually kind of like the way that Lime has this outline better because so this person it had a predicted probability that they did survive, and you could see like here whether or not what features matter the most, and then over on the far right here is the actual the actual value for this person. So sex male is 0, so that means this person was not a male. Sex female 1, this person was a female. Age bin's child, so this person was a child. So this was a little girl here, and so they predicted that she would survive, which would make sense. Well, like I said, women and children off the boat first, and this is both a woman and a child. Now let's come on down to person number 2. The model predicted that the person did not survive with a 93% accuracy, and you can see this person was a man. This person was not a child. I wonder how you get a negative parch. I think that's because I was doing some bad scaling there. But I'm curious. I wanted to see what other age bin it was part of, but apparently I don't have that in here. But anyway, so if you want to learn more about SHAP and Lime and understanding like the black box of like understanding your model, like I do a good job in this blog post explaining that. So feel free to check that out if you'd like to learn more about those. So yeah, that's just why I wanted to bring that up. And so like the Titanic data set is interesting because I was Googling like 2 weeks ago, like how do you get Titanic to give you like a 95% accuracy? And so there was not like one defined way that was like, okay, this is the best Titanic model you can do. But it was interesting, the ones that all seemed to fare better all heavily relied on the features of whether the person was a male or female and what age the person was. So there you go. And in fact, so even SHAP and Lime are basically saying in here, you know, this whether or not the person was a teen or not really didn't matter at all. Like, this was not a very predictive feature. It's like, and as Chap and Lamb are validating here, like male, female. I guess ticket class also kind of had some value in there, but fair really didn't matter much. Yeah, so it's kind of cool to see these things pulled out of the black box and understanding them a little bit better. All right, so model validation is complete. So what do we want to do next? So we can, I just want to show like a simple model export. Simple, I'm gonna break this into a new section, and then I don't know if I want to go, because we're already at 8:15 here, I don't know if I want to go much further tonight. So saving out a simple model. So saving out a simple model, and the reason I say this is, well, let's do this first, and then I'll share what we're doing. So, like I said, so we actually did use the model actively here. So let's say I am building my API later on, and I want to use the model and basically emulate the same functionality. So how do I get this object here out into where I can use it properly? And so that's what we call model serialization. And model serialization is generally done to where like the values and stuff are saved out into what is called a pickle file, a .pkl file. Not every model is saved as a pickle file. A lot of the more basic, like binary classification or regression ones are. It's when you start to get the fancy deep learning stuff that things are kind of different. So in order to save out our model, we're going to use the pickle library. So I'm going to put in here import pickle. So we're going to pickle our file, import pickle. And then we're going to save it out to our directory. So let me just check what I named that directory. So cd ls. All right, so I called it models. All right, so all right, so saving the RFC model to a pickle file. All right, so how you do this is pretty simple. It's basically now I'm struggling to remember off the top of my head. I know it's dump. Pickle.dump. Is it just pickle.dump? I'm gonna have to look this up. I don't remember off the top of my head. Maybe I did it in this notebook, or maybe I didn't. Did I save it out? No, I did not save this out. Okay, no problem. So pickle save model. All right, saving. I usually just pick the first Google result because it's usually correct. Okay, so pickle.load. So pickle. All right, so here's what I was looking for. I knew it was .dump, so it's pickle.dump. Then you put in your model, and then the name of the file. So, and I don't know if you can do it all in one line or not. So pickle.dump. We're going to call so it's our RFC model that we want to save out. So our RFC model, and then we want to save it to the models directory, which is one up and then one down, and then I'm going to save it as RFC model.pkl. And I don't know if this is going to work. Yeah, so I knew that wasn't going to work. So I thought this did work directly. I don't know if something changed recently. I noticed this the other day. Whenever I was playing around. There is a simple workaround for this. So if you recall how we can load in like other data sets using the standard Python stuff. So with open, model, okay, models, models, RFC model.pkl. All right, so the first value is where you want to save it. The second value is going to be RB, which stands for write binary, because we want to write this as a binary file, as F. And we're going to alias that as F. So then we could do a pickle.dump, and then RFC model.pk, and then F. I know it doesn't exist. I'm trying to create it. Okay, I did. I did something wrong. What did I do wrong here? Oh, I'm sorry. It's not RB. It's WB. I think I even said it right because I think I said write binary, but It sounds like it starts with RB stands for read binary, WB stands for write binary. Okay, all right, there we go. So that should have worked. So if we go into our models directory here, now, boom, there it is. There's our pickle file. And now we can, just showing, let's just use this cell here. I'm going to call this loading our trained model. Okay. So I think so I'm going to call this RFC loaded model equals, oh, wait, I'm still in markdown form. Whoops. All right, so loading in the RFC model from pickled, or serialized file. I'm going to call it serialized file. Serialized file. So that is going to be pickle.load, RFC loaded model equals pickle.load, and we want to give it that same file path. So models, RFC pickle, and I think that's all I need to do. Oh, do I need to do this? Okay. All right, sorry about this. So I need to do with open models RFC pickle, and this is read binary, because read binary as f. So again, we're aliasing this. So RFC loaded model equals pickle.load f. So let me delete all this stuff out, f. All right, and getting predictions with the loaded model, just to show you that it works. Loaded model, let's call this loaded preds. Loaded preds equals RFC loaded model dot predict, and then we're going to pass in that same X validation data set again, just to show you that it really is the same thing. And showing the metrics with the loaded preds. So I'm basically going to copy the same thing down here, and I'm going to change out obviously the validation preds to be the loaded preds, and it should be the exact same values. So what do we call this? I'm sorry, loaded preds, loaded preds, loaded preds, and then loaded preds, loaded. And okay, so if we did things right, then it should show up with the exact same values, and it did. Woo! Hot dog. Which makes sense, because so basically it's saying, all right, when you did the loaded preds, you're passing it through the exact same model that you did up here. It's just that we saved it out to this pickle file and then we load it back up. And so the reason I said we were calling it a simple model is because this is just saving out like the trained model itself. Now there is this is something that I do want to get into, but I don't think we're going to get into it tonight just because we're starting to run long. And that is, so if you recall back from from one of our other notebooks here, or the last notebook that we did, so our feature engineering notebook, we had done some feature engineering to get it to this point, and then also had like special like imputers here and stuff. So you can actually do the same thing, the same sort of idea here. You can have pickle files for the simple, like if you want to consistently transform your values at the same time with the simple imputer, you could save that out as a pickle file. For your one-hot encoder, you could save this out as a pickle file. And so and this is not a bad practice per se, or well, let me rephrase that. This isn't an incorrect practice. You could have a bunch of pickle files like this, or scikit-learn offers the functionality to basically take all of these different things, including the train model, and bundle it all into one pipeline with one pickle file. And that we are not going to cover tonight because that takes a little bit to learn. So that's actually probably what we're going to cover next time, is figuring out how to do that. And then we are going to then focus on actually putting this as part of an API. So, and then we'll get out of the Jupyter Notebook world, and we'll go into IntelliJ, which is my IDE. We don't have to use IntelliJ. You could be using VS Code, Atom, whatnot. But yeah, we did some great work tonight. So yeah, that is what predictive modeling is. So it is not necessarily as fancy as you'd think it'd be. Under the hood, if you were to look at all the math, it's doing some pretty fancy stuff underneath there. And this is why like it's super cool that people throughout history have been able to figure out how to do these fancy things with math. And it's interesting that like a lot of these concepts were derived like centuries ago, literally, and it's just now that we're able to apply them because we have these fancy things called computers, and can blast through all these mathematical computations in a split second, whereas these guys were doing stuff by hand way back when, and that's just not possible. Like when you get millions of rows of data, like that's literally millions of calculations. But you saw how fast my little Mac Mini just breezed through that, no problem. So I have a feeling like if I were to invite, I don't know, who's a famous mathematician, I don't know. If I were to pull any mathematician from the 17th century, this would just blow their minds. And yeah, because it is really cool. So yeah, that is all I'm going to cover tonight. We are going to go ahead and wrap up. I don't know when I'm going to do the next stream. I'd like to do another one this week, and I think it'd be fun to do another one. But for now, let me go ahead and push this up to GitHub in case you want to make use of this. So, like I said, I like to do a git status just to make sure, see what we did. Okay, git status. Okay, so we added our notebook and our models. Git add all. Git commit. Adding predictive modeling notebook and RFC simple model. I kind of wish I would have named it RFC simple model, the pickle file. No big deal. And then I'll push it up. Git push origin main. All right, so now if you want to go and look at this, what we did tonight, this exact same work is now up on my GitHub. So if I go to github.com/dkhundley, and then if I go, like I said, we're eventually going to get into working with SageMaker. So I named this Titanic SageMaker BYOC, and we'll talk about what containers are up in the future. But if you just want to see what we did tonight, so go in here, and then there's our notebook from the very first time, our notebook from last time, and then our notebook from tonight. So, and there we go. So there you go. There's the whole web preview of what we just did. And so, yeah, let's go ahead and wrap up. We've been going for about 90 minutes. Just checking the chat to see if there's any questions. Don't see anything, and that's okay. Hope you enjoyed this. Hope you found this one to be valuable. I haven't decided yet if I want to pivot over to the movie thing and take a break from Titanic for the next stream, or if I want to hop right back into Titanic. We'll see. Until then, thank you all for sticking around. I hope you enjoyed this. I certainly enjoyed this. And I'm going to have fun inhaling a bunch of drywall dust tomorrow. But I am so looking forward to having a basement bathroom. So we'll go ahead and wrap it up tonight. Thank you all for watching. Hope you have a great evening. Bye-bye. End stream. Bye-bye.